Today let us take up Fourier transforms, which is another kind of integral transform, and I am going to presume that you already are aware a little bit about Fourier series. So let us start with Fourier transforms. You are aware that if you have a periodic function of a real variable x, then you can expand this in Fourier series in terms of sines and cosines, a whole host of sines and cosines, and you can combine them into a complex notation and write if you have a function that on the x axis has a fundamental interval between a and b, some points a and b, and this is L, then if the function is periodic with this as the fundamental period and then the function repeats itself at intervals of L, then you can write f of x equal to 1 over L summation n equal to minus infinity to infinity some coefficient f sub n e to the 2 pi ni x over L, and these are the Fourier coefficients, and if the function is even, odd, etc., you can write it in terms of sines and cosines, etc., but this is a general Fourier series expansion. Okay. The inversion formula that expresses f sub n in terms of f of x, because this set of functions forms a complete orthonormal set, this thing here is equal to an integral from a to b dx f of x e to the minus 2 pi ni x over L. So this is true for periodic functions. Okay. Now the idea behind a Fourier series, a Fourier transform, is to say what happens if you do not have a periodic function at all. In other words, what happens if I let a go to minus infinity, b goes to infinity, so L tends to infinity, and you do not have a periodic function, what happens to this series here? Well, what happens is that the number of harmonics n becomes a continuous variable, and you have a Fourier integral instead of a Fourier series. So the translation that one has is 1 over L summation over n goes to 1 over 2 pi an integral over whatever you are going to integrate over from minus infinity to infinity dk, say, and then 2 pi n over L gets replaced by this variable k, and that is it. So now one writes f of x, the counterpart of this becomes 1 over 2 pi integral dk e to the power I k x minus infinity to infinity times the coefficients f sub k, but k is a continuous variable and I do not want to write f of k because we have already used f of x, so let us call it f tilde of k. That is my definition of the Fourier expansion, Fourier integral expansion for f of x, and the inversion formula, this formula becomes f tilde of k equal to integral minus infinity to infinity dx f of x e to the minus I k x. So notice that exactly like the Laplace transform, the Fourier transform of a function f of x is an integral transform. So you take f of x, you integrate it with this kernel which is a function of x and k, and out comes a function of k here. Okay. And the development of f of x in terms of the Fourier transform is this integral here with an e to the plus I k x here. Just as in the Laplace transform you had an e to the minus st when you went from t to s, and then you had a plus st in the Mellin formula which gave you the inverse transform. Okay. Now there are lots and lots of conventions in Fourier transforms. There are as many conventions as there are people, I think. This 2 pi can be put, 1 over 2 pi could be put here instead of there, or sometimes you put 1 over square root of 2 pi here, 1 over square root of 2 pi here. Sometimes you make this a minus sign and this a plus sign and all possible combinations of this, but I will stick to this because this follows directly from here with that translation. So the notation is, I mean the convention is not sacrosanct, you can change it, but you have to stick to one convention, otherwise you miss factors of 2 pi. Okay. So the crucial thing that you regard is that you regard the Fourier transform as an integral transform of this kind. Now one could immediately ask, what are the conditions on f of x such that the Fourier transform exists? When would this integral exist? Okay. Well, clearly this is just an oscillatory factor for real values of k. So you would expect that this will certainly exist if f of x is absolutely integrable, that is for sure. So if this quantity f of x dx mod f of x integral from minus infinity to infinity exists, then this integral certainly exists, absolutely. Now that is a sufficient condition, it is not always essential, but it is a sufficient condition. And the two conditions that you need for this to exist are very similar to the conditions you need for a Fourier series expansion to exist. You would like this f of x to have only a finite number, at most a finite number of finite jumps, and it should be in L1, namely it should be absolutely integrable. Okay. So let us put those down as some kind of necessary sufficiency conditions. 1, f of x has a finite number of finite discontinuities and 2, f of x is an element of L1. Okay. In other words, it is integrable, absolutely integrable. We are going to write down Fourier transforms for things like delta functions and so on, which certainly do not satisfy these conditions, but these are sufficiency conditions. Okay. And there is an extensive theory which tells you under what conditions these integrals exist, what are the minimal conditions and so on and so forth. We are not going to get into that right now, but what we need to understand is to specify a given space of functions such that the Fourier transform and the function itself are both in the same space. And it turns out that if you look at the space of square integrable functions, then this is so. The Fourier transform of a square integrable function is also square integrable. And the most important application of this, of course, as you know, is in quantum mechanics, where if you look at the position space wave function of a particle, you want it to be square integrable because that is the total probability, you would like it to be normalizable. And when you do a Fourier transform, you work in momentum space in terms of momentum space wave functions. That too is another physical observable, the momentum itself, and therefore you would again like the wave functions to be normalizable. And it is convenient that since these two are related by Fourier transformation, namely the momentum space wave function is the Fourier transform of the position space wave function, it is good to have the fact that if one is an element of L2, so is the other an element of L2. We will write that down explicitly. Okay. Now having said this about Fourier transforms, having defined it in this fashion, we should also ask what are the analytic properties? Where would such a thing be analytic as a function of k? Well, as it stands here, the question is, can I move off the k axis to the complex k plane and would this still make sense? The answer in general is no, because if you move off the k axis and make it have an imaginary part either in the upper or lower half plane, whichever half plane it is in, x runs from minus infinity to infinity. So in one of the two half planes this thing is going to be an exploding exponential, and that is not good news, right. This immediately means that unless this function f of x cuts off very rapidly for very large values of mod x, such a thing has no chance of existing at all. If this were like a Gaussian, for example, then yes, you could do it, but otherwise if this thing here decreased or fell off at infinity like some polynomial, like some power of kx, then this is not going to exist for complex k. So in general you only have the real axis, unlike the case of the Laplace transform where you had analyticity in a whole half plane. So let us write down simple Fourier transforms of functions and see what this whole thing looks like. So let us start with a function like a very familiar function. So let us put f of x equal to sine bx over x. be real. Okay. This is going to give us the Dirichlet integral. I am going to use that. By the way, this function has a name in engineering. It is called the sinc function, and you know what it looks like. It has got a maximum value which hits b here, and then for positive b for instance, and then it goes down like this, and this amplitude here decreases like a 1 over x. The magnitude the modulus decreases like 1 over x. Okay. Now what does the Fourier transform do? Well, we can write this down immediately. F tilde of k equal to integral minus infinity to infinity dx e to the power minus ikx and then sine bx over x. And what does that give us? Well, this is a cosine kx and then a sine kx, but the sine kx part is going to be an even function in the numerator and an odd function here, and this thing is going to be 0 by symmetry. So the only thing that contributes to a non-zero extent is the real part. So this is equal to cos kx sine bx. So let us write this as 1/2 integral minus infinity to infinity dx. Sine bx cos kx is sine b plus kx over x minus a plus sine b minus kx over x. Okay. And that is the Dirichlet integral. We know how to do this integral. That is equal to pi over 2 from 0 to pi, but now we got a minus infinity to infinity instead of 0 to infinity, so it is equal to pi itself. So it is a half and then a pi the sine of b plus k plus the sine of b minus k. By this I mean plus 1 if b plus k is positive, minus 1 if b plus k is negative. And what does this thing look like? Well, let us just plot this. So here is k, here is minus b, and it says if b plus k is positive, so b is greater than k is greater than minus b, it is like this, and then a minus sign, minus 1. This is 1 and this is minus 1 out here. And the second factor, the second term here is sine b minus k, so it is equal to 1 as long as k is sufficiently negative, and then it is this, and this is at b. And what we got to do is to add up these two guys. Now I add this to this, and the minus 1 and plus 1 cancel, and out here the plus 1 and minus 1 cancel. So this Fourier transform is non-zero only between minus b and plus b. So what does it look like? F tilde of k equal to, and in between the two it adds up to 2 there, and that cancels this half here, so it is equal to pi times a pulse which is 0 all the way from minus infinity, and then does this goes, and this is unity, this is minus b, that is it. So that of course we know how to write that. That is equal to theta of k plus b minus theta of k minus b. So if k is large positive, it is 0, because if k exceeds b, this gives you a minus sign and kills this out here, and if k becomes less than minus b, this kills that. So it is just a pulse function, unit pulse function between minus k, minus b and plus b. So what is the lesson? It is telling us that if this function f of x dies down like 1 over x roughly, then the Fourier transform is quite compact. Now 1 over x is a very slow decay, barely converges, the integral barely converges, and this whole thing, in fact this integral from minus infinity to infinity is only conditionally convergent, it is not absolutely convergent. So if in X space the function is quite spread out, then in K space the function is, the Fourier transform is very compact. Okay. Let us look at another example and see what, suppose in X space the function dies down a little faster, say it dies down like 1 over x squared, say, then what happens? Oh, by the way, I should point out something here before I go further in this. Remember that f tilde of k equal to minus infinity to infinity dx e to the minus ikx f of x. Very often we are going to be concerned with cases where f of x is a probability distribution, a density function by itself. In other words, it is non-negative and it is normalized to unity. We are going to look at that case in particular. What is this equal to then? This is, if this is a probability density, and let us for the moment call it P of x, probability density, then the Fourier transform of that probability density P tilde of k is given by this, but that is also equal to the average value of e to the minus ikx, because it is the weighted average, weighted with the probability density, and just the statistical average over this probability density of e to the minus ikx. But I can expand that and write this as equal to a summation n equal to 0 to infinity minus ik to the power n over n factorial, and then the average value of x to the n. So it is essentially generating all the moments of this distribution. So the knowledge of this function, if you extract the coefficient of k to the n in a power series of this function, that coefficient is, apart from this I to the n over n factorial factor, it is the average value of x to the n, the nth moment of x. So the Fourier transform of a probability distribution is called its characteristic function, and the characteristic function generates all the moments for you once you expand it in a power series. It is a useful piece of information to have. We are going to use this fact later on. Okay. So this thing here is called the characteristic function. Okay. Now of course this example here, this is not a good probability distribution density function. Why is that? Yeah, it is not positive definite, it is not non-negative, it has got plus and minus values and so on. But its Fourier transform was the uniform distribution between some minus b and b. And which one you call the Fourier transform and which you call the original function is kind of arbitrary, right. So if you look at a uniform distribution, its characteristic function is this. So imagine I started with a pulse in x, and then in k space it would look like this, sin bk over k or something, sin k over k kind of thing. And from here you can generate all the moments of this uniform distribution. In this case let us look at, I was going to look at a function f of x which died down a little faster than 1 over x, and let us look at a probability distribution itself. By the way, if I choose this to be 1 over x squared plus some lambda squared and normalize it, so let us write it as lambda over pi times x squared plus lambda squared, where lambda is some positive constant. This is a Lorentzian shape, it is called the Cauchy distribution, the symmetric Cauchy distribution. And what does it look like? Well, this thing looks like a sort of bell shaped thing, dies down like 1 over x squared at this point, and the width is related to this lambda. If I integrate this from minus infinity to infinity, it is twice the integral from 0 to infinity, and 0 to infinity is 1 over lambda, which will cancel this, tan inverse x over lambda, and only the infinity part will contribute, that will give me a pi over 2, the pi will cancel. So it is normalized. Okay. Now what is the Fourier transform of that? So given that, what is f tilde of k? Now we can do this fairly easily. So given that, let us look at P tilde of k, since I use that notation. This is equal to lambda over pi, an integral from minus infinity to infinity dx e to the minus I kx over x squared plus lambda squared. Okay. And it is tailor made for using contour integration, right. It is just the sort of thing we can do by contour integration. Where are the singularities of the integrand in x? Well, there is one at I lambda and another one at minus I lambda, and the contour of integration runs like this. Now, when k is positive, this is a positive number, then I need to close this contour in the lower half plane, so that I would get when k is positive, if I put x is plus I something or the other, it blows up in the upper half plane if x has a positive imaginary part, and it goes to 0 in the lower half plane. So I need to close it in the lower half plane. And then what happens? So first let us look at p tilde of k. For k positive, this is equal to lambda over pi, and then I am going to close this with a contour in this fashion and pick up the contribution from this pole minus lambda I lambda, right. So it is going to be, I am going to do this in the wrong sense, in the negative sense. So there is a minus 2 pi I, and then this is x plus I lambda, x minus I lambda, and I am picking up from x minus I lambda. So this is divided by minus 2 I lambda e to the power minus I k into minus I lambda, which is equal to the lambda cancels here, the minus cancels, the 2 cancels, the pi cancels, everything cancels out, and you get e to the power minus k lambda. Okay. If I closed it, if k were negative, I am forced to close it in the upper half plane, and then the same thing would happen. You get a lambda over pi, but now I have a plus 2 pi I, and then I would have a plus 2 I lambda here because the pole is at plus I lambda, so this part does not contribute, and be a plus I lambda, and you get e to the k lambda, but k is negative. So this means that in both cases I could write this as equal to e to the minus mod k times lambda. Okay. So you have to be careful which way you close things, and you have to be very careful because in this case it is clear this is not an analytic function of k, it has got a modulus sitting there. Even as a function of a real variable, this function is not differentiable at k equal to 0, it has got a cusp at k equal to 0. But it tells us an important lesson. We saw that if this function, if the function in x went off, died down like 1 over x, then the Fourier transform was fairly compact. Now this function is dying like 1 over x squared, and what has happened is instead of a very compact Fourier transform, you got something that is decaying exponentially. So that spread out because the function in x got a little more compact. So let us look at a Gaussian and see what happens, and that is a case which you need all the time. So let us look at f of x, which could also be a probability distribution. We may as well take it to be a normal distribution, 1 over square root of 2 pi sigma squared e to the power minus x minus mu squared over 2 sigma squared. This is a normalized Gaussian distribution with mean value mu and variance equal to sigma squared. Okay. And what is p tilde of k in this case? Equal to. By the way, what should p tilde of 0 be? If it should be 1. If this probability distribution is normalized, it should be 1. So there is no factor sitting outside, all that will get cancelled out, and as you know, the Fourier transform of a Gaussian is a Gaussian itself. It is a very standard integral to do, and this thing turns out to be e to the minus k squared over 2 sigma squared minus I mu k. Check this out. all you need to do is to use the elementary formula for the Gaussian integral. The important thing is that this here, which told you what the width was in x space, appears in the numerator here. So this is telling you that the Fourier transform of a Gaussian is a Gaussian, but if it is very narrow in x, it is very broad in k and vice versa. And it very neatly moves it up here. This is going to have a lot of significance. Later on we are going to look at what is called the Poisson summation formula, a very crucial thing, and this factor will play a crucial role also. By the way, carried to an extreme, again since we are talking about quantum mechanics all the time, carried to an extreme, this thing here, this Gaussian, if I make it thinner and thinner such that it approaches like something like a delta function, which means a position eigenstate at one point, you would expect the momentum uncertainty to become infinite, and that is exactly what is happening, because if this thing here approaches 0, this width here becomes broader and broader, approaches infinity. In fact, this thing is exactly a minimum uncertainty wave packet, but we will come back to this a little later. So we see now that compactness in one variable means broadness in the other variable and vice versa, in the conjugate variable and vice versa. This is at the very heart of the uncertainty principle in quantum mechanics. Now what I did not mention was that if you have f of x an element of L2 minus infinity to infinity, in other words, if this is true, minus infinity to infinity dx mod f of x whole squared is finite, normalizable, some number, then it turns out, I mentioned that f tilde of k is also an element of L2, and in fact it turns out that this is exactly equal to, with our convention for 2 pi's, and this is an example carried over to Fourier integrals from what we already know from Fourier series. This is called Parseval's. It essentially says that one wave function is normalized and the other wave function is also normalized. Okay. But Parseval's formula is true in general, I mean it is true for any function in L2. The Fourier transform mod squared integrated is equal to this here. Okay. What else? Well, we also have the convolution theorem, I should mention that. Okay. So if you have minus infinity to infinity dx prime f of x prime g of x minus x prime is a convolution of the functions f and g, then the Fourier transform of this, let us call that f in this fashion, equal to the Fourier transform of f times the Fourier transform of g. That is the convolution theorem. For Fourier transforms. We saw there was a similar theorem for the case of Laplace transforms. There the integral went 0 to t, but this is now minus infinity to infinity. Okay. By the way, it is also true in the converse thing. So if you have a convolution in k space, then when you invert the transform you are going to get the product in x space, apart from some 2 pi factors. Okay. This relation, Parseval's theorem formula, is itself a special case of a slightly more general formula, and that is the following, easily established dx. So if you have a function f of x and another function capital F of x which has a Fourier transform, etc., and you consider this integral little f of x capital F of minus x, then this is equal to integral minus infinity to infinity dk, or there is a 2 pi f tilde of k f tilde of k. Okay. So, exercise, show that this is true. It is fairly straightforward, you just need to use the fact that the delta function has a Fourier representation. You need to use the fact that delta of x equal to 1 over 2 pi integral dk e to the I kx, which of course implies that delta tilde of k equal to 1. The Fourier transform of the delta function is 1 with the normalization we have chosen. So, what you need to establish Parseval's theorem itself, formula itself from this is very straightforward. All you have to do is to set f of minus x equal to f star of x. Like this. This will immediately imply Parseval's formula. From this, it will immediately imply. But this is an easily established result. So, you should first establish this and then look at this special case. What would this imply for the Fourier transform f tilde of k? What would it imply? So, let us write that down. This would say f tilde of k equal to integral minus infinity to infinity dx e to the minus I kx f of x. Agreed? But let us change k to minus k. Let us change x to minus x in the range of integration. So, this is also equal to integral minus infinity to infinity dx e to the I kx f of minus x. I change x to minus x, but I have now set f of x minus x equal to f star of x. So, this is equal to integral minus infinity to infinity dx e to the I kx f star of x. Okay. But that is the complex conjugate of the Fourier transform of f of x. So, this is equal. And then you got Parseval's formula for this. Okay. So, just simple tricks of this kind, changing x to minus x, etc. Okay. Now that we have done this much, let us do something interesting. Let us ask what happens if I apply this Fourier I want to find a little more about this Fourier transform operator. It is an integral operator, that much is clear, but I would like to know what sort of integral operator it is, some properties of it. And one of the things about operators is you ask the first thing you ask is what happens if I apply it a second time, third time and so on. So, let us apply the Fourier transform operator twice in succession. So, I take the Fourier transform and instead of taking the inverse transform I take the Fourier transform once again. Then what happens? Well, so I take some function f in the space, I am going to work in L2 all the time and I apply the Fourier transform operator to it, and let us call the result some function of x. This thing is equal to, by definition, minus infinity to infinity dy e to the minus ixy f of y. Y is integrated over and I get a function of x. So, this is f acting on f acting on this function f and expressed as a function of a variable x, that is equal to this guy here. So, I want to act once again on it. So, f squared f of x equal to an integral minus infinity to infinity dz e to the minus I xz, not f of y but f tilde of z. So, dy e to the minus I z y minus infinity to infinity f of y. right, which is equal to an integral from minus infinity to infinity dy f of y, and then an integral minus infinity to infinity dz e to the minus x plus y times z, I times that. But we know what this is. It is just 2 pi times the delta function, right. So this is equal to 2 pi times minus infinity to infinity dy f of y, a delta function of x plus y. Notice the plus in there, which is equal to 2 pi times f of minus x. So what's happened is that if you take some function and you apply the Fourier transform operator twice, all you are doing is to change x to minus x apart from this factor 2 pi. But we know that if you apply the parity operator to a function, you change x to minus x in that. So this tells you that f squared is essentially 2 pi times the parity operator. By that I mean Pf on x equal to f of minus x. So remarkably enough, apart from this 2 pi factor, which incidentally arose because of our Fourier transform convention, had I chosen 1 over square root of 2 pi for defining the transform either way, this 2 pi would have gone away, and you would have found out that the square of the Fourier transform operator is the parity operator. So in some sense, if you ask what is the square root of the parity operator, it is the Fourier transform operator. Very weird. I mean, parity operator changes x to minus x in this function, but the Fourier transform is some integral transform, some crazy integral operator, and yet its square is equal to the parity operator from this. What happens if I take the square of this operator once again? What is the square of the parity operator? The identity operator. So this is telling you this really weird result that f4 equal to 2 pi whole squared times the identity operator.